In this video, we're going to look at solving equations involving sine, cos, or tan. It's easier for most people to think about angles in degrees rather than radians, so in this video I'm just going to work in degrees. Let's say we wanted to solve sine of theta equals a half. That means we need to find all the angles theta with a sine value of a half. Remember that on a unit circle, the sine of any angle is the y value of the point on the edge of the circle. So for instance, sine of 58 degrees is about 0.848. If you are happy and able to use a calculator, you could find one solution to this equation by just typing in sine inverse a half and getting 30 degrees. But this is one of the values you really should know without a calculator. To be successful at trigonometry, you should learn the exact values of sine, cos, and tan for 30 degrees, 45 degrees, and 60 degrees. I won't go through them in this video, so if you've never seen them before, then you'll just have to trust me for now that these are the right values. Looking at the table, you can see that sine 30 degrees is a half. Looking at the unit circle, we can check that sine 30 degrees equals a half too. So one solution to the equation is theta equals 30 degrees. By considering the unit circle, you can see there'll be another solution too. We want the second coordinate of our point to be a half. So if we look at the graph of y equals a half, there are 2 points where this line crosses the circle. One is at 30 degrees, which we saw earlier, but the other one is reflected over into the second quadrant. So let's go over to 180 degrees and work backwards 30 degrees. So another solution to the equation is theta equals 150 degrees. These are the only 2 points on the circle with a y value of a half, but that doesn't mean there aren't other values of theta with a sine value of a half. Remember, you can go all the way around the circle and get back to the same point. So taking our angle of 30 degrees, we could add 360 degrees, bringing us to 390 degrees. And we can do the same thing with the solution 150 degrees to get theta equals 150 plus 360, which is 510 degrees. Obviously, we can keep on adding 360 degrees to these two basic solutions and we'll get more and more solutions. 750 degrees, 870 degrees, and so on. Also, going back to the very first value of 30 degrees, we can take away 360 degrees, giving negative 330 degrees. And from 150 degrees, we can also go back around 360 degrees to get negative 210 degrees. It should be obvious that we can keep adding or subtracting 360 degrees from the first two values, so there are going to be infinitely many solutions to the original equation. Rather than just listing lots of values, we can describe the solution in general. The first group of solutions is 30 degrees plus or minus some multiple of 360 degrees, which we can write as theta equals 30 plus 360n, where n is an integer. Z here stands for the set of all integers, positive or negative or 0. And the second group is 150 plus or minus some multiple of 360 degrees. So we can write that as theta equals 150 plus 360n, where n's an integer. Note that n can be negative, so a solution like negative 210 is just 150 plus 360 times negative 1. Although I focused on the unit circle, it can be helpful to see the solutions to this equation on a graph. So let's graph y equals sine x and y equals a half. You can see that they intersect at x equals 30, x equals 150, 390, 510, negative 210, negative 330, all the solutions we found to the original equation. It's also obvious that you can get more and more solutions by adding 360 degrees, because that's the period of the sine graph. Let's look at how the method shown could be adapted to solve equations with cos or tan. Consider first cos theta equals a half. Again, this is an exact value you're expected to know, so you can get the first solution of theta equals 60 degrees. Have a look at this unit circle again with a 60 degree angle. Where else is there going to be a point with an x coordinate of a half? That is, where else will the line x equals a half intersect with the circle? Hopefully you can see that the other point is a reflection in the x-axis, down at negative 60 degrees. If you thought of this as 300 degrees, then that would be perfectly okay too, because you get to the same point by going around the circle the other way. Once you have these two basic solutions inside a unit circle, you can just add or subtract 360 degrees to get more solutions. The general solution is going to be theta equals 60 plus 360n and theta equals minus 60 plus 360n. And in fact, you could write it just as theta equals plus minus 60 plus 360n. Let's now look at the equation tan theta equals square root of 3. Again, the basic solution should be known from your exact values. Theta equals 60 degrees. Where else in the unit circle is there going to be a line segment with the same gradient? Well, it's not going to happen if you just reflect in the y-axis, which is going to give a negative gradient of negative root 3. And it's not going to happen by reflecting the x-axis, also with a gradient of negative root 3. But what you could do is rotate the original segment around 180 degrees. And you can see it has a positive gradient, and it's the same as the original line segment, that is, a gradient of square root 3. So the second solution is theta equals 60 plus 180, which is 240 degrees. Again, from these two basic solutions, we can keep adding 360 degrees to get more solutions, like 420 degrees and 600 degrees, and so on. So we could write the general solution as theta equals 60 plus 360n and theta equals 240 plus 360n. But actually, if you think about what we did here, we just took 60 degrees, added 180 degrees, and then we can keep adding 180 degrees to get around half a circle each time. So a better way to write the solution is theta equals 60 plus 180n. You might have noticed that in every equation solved so far, the right-hand side was an exact value, like a half or root 3. But what could you do if you had a value that wasn't on the exact value table? If it's just the negative of something that is on the table, you can still solve the equation. But first you need to use a bit of symmetry to find the first two solutions. For instance, given sine theta equals negative a half, you can use the fact that sine 30 degrees equals a half. So by looking at the unit circle, the two solutions are in the bottom half, at negative 30 degrees and 210 degrees. The general solution can be written as theta equals negative 30 plus 360n and theta equals 210 plus 360n. Or with something like tan theta equals negative root 3, you know that tan 60 degrees equals root 3. So you could take the solution negative 60 degrees, which has a gradient of negative root 3. This gives the general solution theta equals negative 60 plus 180n. If the right-hand side is some value that doesn't resemble anything in the exact value table, then you'll probably have to use a calculator to get the first value to get started. For instance, to solve cos theta equals 0.3, a calculator will tell you that cos inverse 0.3 is about 72.54. So that's our first solution. Then, by symmetry, another solution is at negative 72.54. So the general solution is theta is about plus minus 72.54 plus 360n. In all the examples so far, we've just had theta in the brackets by itself. Now let's look at what happens if you have to solve something like sine 3 theta equals a half. It's best to avoid trying to think about what 3 theta would mean inside the unit circle. Instead, the easiest thing to do is to introduce a new variable like u and define it to be 3 theta. Then you can just solve sine of u equals a half and convert the solutions back to get values of theta. The general solution was u equals 30 plus 360n and u equals 150 plus 360n. And dividing everything through by 3, we get theta equals 10 plus 120n and 50 plus 120n. If you wanted to list a few values, you can sub in different integers for n. If n equals 0, you'd get theta equals 10 degrees and theta equals 50 degrees. For n equals 1, you'd get 130 degrees and 170 degrees. For n equals minus 1, you'd get negative 110 degrees and negative 70 degrees. And obviously you can keep going to get more and more solutions. Let's summarize the method for solving trigonometric equations. First, you need to find one solution in the unit circle, either using the exact values table or a calculator. Let's say this first angle is a degrees. Next, you can find a second solution in the circle using symmetry. If you want to keep the same sine value, which means the same y coordinate, you should reflect in the y-axis by taking 180 minus a degrees. If you want to keep the same cos value, which is the x coordinate, reflect in the x-axis, which is the angle negative a degrees or 360 minus a degrees. If you want to keep the same tan value, which is the gradient, you can rotate around half the circle, which is 180 plus a degrees. Once you've found the 2 points in the circle that solve the equation, you can keep going around by adding and subtracting multiples of 360 degrees. Your final answer could be given as a general solution, or you might be asked to just list all the values that fit within a restricted domain. The process of solving trigonometric equations can be a bit confusing when you first start out, but hopefully this video helps you to understand the basic method.